I checked the weather report here in Baltimore. If there's snow tonight, it's not going to happen it's supposedly not going to happen till after 11 o'clock. So we finish at 9:30. You should have plenty of time to get home unless you drove 2 hours to get here, in which case I applaud you, okay? All right. One more minute. Just give a second. I won't be ready.
How much your son's go? Oh, don't say I don't want to. That great stuff. I mean, we're looking midday, right in the sun. Everything.
Just for you. Okay.
I have an old switch. That's very nice. I had an 8. I had that original orange tube. Orange tube. And it did some nice stuff. The problem is, it's really mountain. But I was looking at this. I had a
breeze blowing in.
All right. Calvin, we ready? You got the thumbs up. Okay. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach. And when you came in, there are lithographs on the table here. Our lithograph tonight is the Eagle Nebula M16. These are the pillars of creation in the Eagle Nebula, seen in both visible light and infrared light. And this will have special significance for our talk about infrared telescopes tonight. Our talk is, it's not working. All right, so let's go here. Our talk is Webb in 3 acts: the telescope, the science, the legacy. And we have 3 speakers to take care of those 3 parts. And I'll introduce them later, but we're going to get a good look at the James Webb Space Telescope tonight. Next month, we have The Wildest Weather in the Universe by Hannah Wakeford. And in that, she's not talking about just in our solar system, but also in other planetary systems, the planetary systems that we have found, and the weather that we would deduce happens on those planets. On March, we have Mia Bovil coming back again. She's given some wonderful talks the last couple of years, and she decided she was going to have some fun with her title. So it's called Mapping the United Federation of Planets, an Astronomer's Guide to the Galaxy. So she will be using lots and lots of Star Trek references, okay? But she will also be putting them in context of our actual scientific knowledge of the galaxy. So if you want a combination of fact and fiction, come to see in March. In April, Susanna Deustoa is going to talk, and she did not give me an actual topic. She just said, I'll talk about something about cosmology, because everybody loves cosmology. So in the next month or so, I will get an actual title out of her. But you guys do love cosmology, right? Yeah, so you're going to come no matter what. All right, great. If you would like to keep up with what's going on, you can Go to our website. If you just put in your favorite search engine, Hubble Public Talks, you'll find this web page, and you can see we've got a list of the upcoming lectures. We've got links to the webcasting, which are live when we are doing it live now, as well as links to the past lectures. We've been on YouTube since spring of 2014, and we have been on the STSCI webcasting site since 2005. So we're approaching 13 years of astronomy lectures on our webcasting site. That's one of the reasons I ask you all to give a hand to our webcasting folks at the beginning, because they do such an amazing job in archiving these wonderful talks. You can also sign up for our email list that will send you reminders of the talks every month. This is the email one, which is sort of redundant now that we have the sign up on our webpage. You can also, however, send us comments and questions to publiclecture@stsci.edu. Social media, we have Facebook, we have not one, but 2 Twitter accounts. We have YouTube. We have Instagram. We actually ought to get the JWST ones up on here now that we're getting closer to JWST launch. So, yeah. All right. My apologies. It'll be fixed for next month, okay?
That's good. Using Space Telescope for right now.
Using Space Telescope right now. I also occasionally post on a blog and Facebook, Google+, and Twitter, and you can get those if you like. Across the street, we have the Maryland Space Grant Consortium Observatory. The Maryland Space Grant Observatory will not be open tonight. If you looked up, you didn't see many stars, if any, on your way in. It's cloudy. Actually, the fact that it's cold is really good, because when it's cold, the air is still, and it'll be a really good night. I mean, some of the best nights observing are when you're totally freezing your butt off, okay? Unfortunately, clouds are never help, whether it's cold or warm, so they will not. They do have open houses on Friday evenings. If you go to md.spacegrant.org, they have this page here where you can find the observatory status. They will post it by like 6 or 6:30 on every Friday as to whether they're opening up on those Fridays, okay? So come back to it and visit us in future lecture series, and maybe it'll be open, but certainly you can try every Friday on that. And now the news from the universe for January 2018. Our first story is a month old. It is our Yuletide stars. So every year we have to put out something for holidays, right? And they go through a selection process and they come up with something. And this year they came up with the globular cluster Messier 79. And this was brought up in our news meeting, and they said, okay, what can we do with this to make this holiday? And we were batting around ideas, and I came up with something. I said, well, you know, we could do this thing that we did, and I'm not going to tell you the idea because it'll show up in just a second. I said, yeah, you know, that might work. And they held me to it. So I came up with an idea in the middle of a meeting, just off the top of my head, and they made me follow through in it. So the team and I got together, and we put together a little visualization of this globular star cluster with a surprise holiday theme at the end. So this is one of our normal zooms in on the night sky to show you where Messier 79 is. And it really is deeply hidden. There we start to see the cluster. This is a ground-based version of it. But as we zoom in, you find out that Hubble doesn't see that wide field version. It doesn't even see this version. It sees the very central region of this globular star cluster. And to give you a feel of the 3D, we created this 3D visualization. It has the similar statistical properties as this M79 globular star cluster. And then as we pull out, our idea of a stellar snow globe is revealed. So this will teach me to speak up during meetings. We also created this version, which is just the snow globe spinning, and it actually is on a loop. So you could put this in the background of your holiday party next year, and you could have that snow globe spinning infinitely with the holiday season greeting on it as well. Our second story tonight, finding defects in the star formation factory. Yes, there are people who have to find those defects. All right, so this is the star formation factory I'm talking about. It's called the Orion Nebula. And this is a star-forming region, and there are several thousand stars, about 4,000 stars, that have just formed. And when we say just formed, on astronomical timescales, that's 2 million years ago. Okay, so there are stars in the Orion Nebula that are 2 million years old. But not all things that collapse are massive enough to form stars. Okay, so if this is a star formation factory, sometimes you get some defects that are too small to form stars. Right? And it's important for us as astronomers to try and understand when you've got a collapsing nebula, you've got a gas cloud that's collapsing to form objects, what percentage of that material goes into stars? What percentage of the material goes into planets? We really want to know that too, and we're searching that in other ways. But what percentage of it goes into something that's bigger than a planet, but smaller than a star? And that's what we call brown dwarfs, okay? Brown dwarfs range from basically 15 times Jupiter's mass to about 70 times Jupiter's mass, okay? Something that's, that's when you get what we call deuterium fusion. Okay, now the main sequence stars are powered by hydrogen fusion. The fusion of hydrogen into helium is what powers the sun and other main sequence stars. But deuterium, which is called heavy hydrogen, that is not a long-term sustained fusion. It will flare up, it will last for a while, and then it will fade away. So these brown dwarfs are extremely faint, and compared to stars, they're extremely cool. They're so cool that water molecules will form in their atmosphere. And you can actually detect them by looking for water molecules. And where do the water molecules show up? In the infrared. So this is just a single filter from Hubble in the near infrared. And those circles are around certain detections of these brown dwarfs. Now, what they did is they looked in the water vapor line to find 1,200 really red candidates, okay? Candidates that could have brown dwarfs. And what they were really looking for was finding those faint red stars that had brown dwarf companions around them, okay? Because you often get companions. And they found 17 brown dwarf companions around these red dwarf stars, as well as 3 planetary mass companions, 3 that were below the level of the brown dwarf mass and into the planetary mass. Now, those are only candidates, okay? They can't confirm those. Matter of fact, all 17 are candidates, but in talking with one of the researchers, he said there's like a 95% confidence level in all 17 of them that they are actual brown dwarfs. It's the planetary ones that are really small that they can't be totally sure about. So these are their locations, and if you want to see what they look like, this is the highly processed images. Yeah, really difficult. Oh, my laser pointer isn't working. Sorry about that. But what you see in each of those images, on the left is the star, and on the right is the small pixels of the brown dwarf companion. All right, and so you can see the star itself is only about 5 or 6 pixels across, and the brown dwarf companion is only 1 or 2 pixels across, and the detector. And those are still actually unresolved. They're really smaller than an individual pixel at that scale. So you're really having to work deep into the data to be able to pull this out. But hey, that's what science is. At the cutting edge, we don't get gorgeous pictures. We just get these little tiny little pixel things and being able to pull out these brown dwarf companions. Now, needless to say, this will change immeasurably when we have the James Webb Space Telescope that has Hubble resolution, but in the infrared wavelengths, and can see these much more clearly. And I would tell you all about that, but that's the job of our speakers here tonight. So I'll leave it to them to discuss how the James Webb will take this and take it to the next level and really get good census of the brown dwarfs in the Orion Nebula. All right, so now I move on to our featured speakers tonight. They are Bonnie Meinke and Klaus Pontoppidan from the JWST Mission Office, as well as Alexandra Lockwood from the Office of Public Outreach. And I didn't memorize their titles, so Bonnie gave me a title that they are just absolutely amazing people doing amazing work here at the Space Telescope Science Institute. So ladies and gentlemen, an amazing team to discuss the James Webb Space Telescope. Give me a hand.
Does this work? Yeah. Good. All right, so my name is Klaus Pontoppidan. My official title is Deputy Project Scientist for the James Webb Space Telescope here at the Institute. Bonnie has the same title. And Alex is the communications lead for public outreach for JWST. So what we're going to do with this talk here is we're going to tag team it. We gave it 3 titles. The telescope, the science, and the legacy, and I'm going to do the telescope, and then after that, I'm going to give it over to Bonnie to talk about the science, and then Alex to talk about the legacy. All right, so just to introduce this, you may have seen these before, I'm not sure. What do we do at the Institute here, and how is it related to the Webb? Well, an institute has existed for decades now, supporting the operations of the Hubble Space Telescope, as you all know very well. We're operated by an organization called the Association of Universities for Research in Astronomy, or AURA for short. And we're basically a NASA contract. And NASA contracts us to run the science part of its astronomical space missions. As is true for Hubble, it's true for the Wide Field Infrared Survey Telescope, and it's true for the James Webb Space Telescope as well. And so another way to look at it in terms of roles here is that you need to do many things to make an astronomy mission. Right, you have to have oversight of the mission and the policy. Somebody has to drive it from the get-go. So NASA is doing that, and the James Webb Space Telescope is a partnership with the European Space Agency and the Canadian Space Agency. And so they provide the oversight and the policy. Of course, you need technology. You're not going to have a space telescope unless you have some hardware. And so that is built in the case of James Webb by Goddard Space Flight Center, just south of here, as well as partners from the industry. Northrop Grumman is the prime contractor for James Webb. And also other partners like Ball Aerospace. But then, of course, you need science, right? Without science, all you have is a piece of machinery. And so the Institute here is responsible for operating the telescope for scientists. We are the interface between the observatory and the international astronomical community. And it's the same as for the Hubble Space Telescope. So anything that has to do with science is centered at the Institute. All right, so the telescope. So we have the Hubble Space Telescope. You all know that very well, and we love that very much. You're all familiar with the beautiful data and the beautiful images that Hubble has returned. So these are all Hubble images taken in the visible wavelength range. In the optical, visible with our eyes, and has been operating for many years. Now, isn't this awesome? What more do you need than this? How do you do the next big thing? What is that going to be? So some of the things that Hubble has been doing and really showing us are these deep fields of galaxies, high redshift galaxies to enormous distances in the universe, and it looks back in time, of course, to not quite the beginning of the universe, but close. And deep exposures with Hubble has revealed faint galaxies at the edge of detection here. This is related to the original concept of the James Webb Space Telescope, as it was conceived already back in the mid-90s. It was realized that if you want to go really to the back to the beginning of the universe, you have to take into account cosmological redshift. Right? So essentially what happens is when the galaxy emits light, and as that light travels through the universe, the light stretches and becomes redder. And by the time it reaches to us, it can be quite red. And if the galaxy is old enough, if the light was emitted long enough ago, that means if the galaxy is far enough away, that redshift, that cosmological redshift is large enough to shift that light out of the wavelength range of James Webb. Right? It becomes too red, it becomes infrared. And basically the galaxy disappears from view of Hubble, and you no longer see it. And in order to see that galaxy, you'd need a sensitive space telescope that operates at longer wavelengths than Hubble in the infrared. And that was the original impetus for James Webb. It was to be able to see the first galaxies, the first light in the universe, by going to the infrared, to see the most redshifted galaxies. Now, of course, today, this is decades ago, other people have looked at this telescope and gone like, well, you have this big infrared telescope and you could do this awesome science. When this was first started, there was no such thing as exoplanets, and now we have thousands of exoplanets. And so a lot of work has been going into James Webb to make sure that it can also get great data in the area of exoplanets. And this goes on and on for many, many different science areas. All right, so let me say a few more things about the infrared here. So here we have just a visible rainbow, just to give you some context. From blue to red, high energy, low energy, short wavelength, long wavelength. Of course, this is only a very, very small part of the electromagnetic spectrum. To the high energy side, you have ultraviolet, radiation, X-rays, gamma rays. These are all wavelengths that are very unhealthy to humans. So you don't want to expose yourself too much to those because they break chemical bonds and can give you all sorts of nasty effects. Going to the other way, it's low energy. You get infrared microwave. You can heat your food, but it's not going to break your molecules apart. So it's a lot safer. Point here is that the visible is only a tiny, tiny fraction of the infrared spectrum, of the electromagnetic spectrum. And so James Webb is going to give us a lot of the infrared, or access to that. And so here's an indication of that. Here we have the range of Hubble. It goes out a little bit into the near infrared, around to about 1.8 micron or something like that, and then it stops. JWST is going to be a little teeny bit into the visible. Actually goes down to about yellow light. And then it's going to go way into the infrared, beyond the near infrared, what we call the mid-infrared or the thermal infrared, out to 28 micron and a little bit. So in terms of grasp, there's actually a wider grasp in terms of wavelength for JWST than for Hubble. So there's a lot of things in there. All right, so people got, back in the mid-90s, got together and thought, like, okay, so how do we do this? And there's a number of challenges with making an infrared space telescope, and it's not going to end up not going to look like Hubble. So this is an early sketch, actually, essentially on a piece of napkin, considering what such a space telescope might look like. Well, for one thing is there had to be a large mirror in it, and so you can see this here. You can see a deployable mirror. This here doesn't even have a filled aperture. There's actually gaps in between. And the idea here is that you have something that was folded up and folds out once you're in orbit, so you can fit into a rocket. So that's one thing to note about. Another thing to know about is there's no baffle, right? So Hubble is enclosed into a tube. In order to make this deployment here, you couldn't have a tube around it, so there's no baffle. And the final thing to note is this big thing that it sits on, and that's a sun shield. And the reason you need a sun shield is that to have an infrared telescope that is sensitive, that can see faint things, you need it to be super cold. Really, really cold. Hubble is kind of room temperature. This has to be much, much, much colder, and we'll go into that in a little bit more detail. So in order to keep this cold, you can't have sunlight shining directly on it. So you have to have this big insulating shield to protect it from the sun. It also means that there's some limitations in where you can point, because you can't turn this to face the sun. I mean, if the telescope itself would ever see the sun, it would heat up and ruin your day. All right, so what we have now today is something that looks more like that. It comes from the napkin, ends up like this here. And so you have to go far away from both the Earth and the Moon, because the Earth is like a big heat lamp as well. And so it goes 1 million miles away from the Earth down to a point in space called L2, which is a point of balance between the gravitational field of the Sun and the Earth. But I find it fascinating that from that old drawing and to what it looks like today, I mean, you can kind of recognize it. It has the elements, it has no baffle, it has a deployable mirror, and it has a big sun shield. All right. So let me talk a little bit more about sort of the general application of infrared as well. And so Frank talked a little bit about that just earlier. Like one thing is you can see very faint galaxies, but you can do so much more than that. So hey, here's an example here. You can look at the formation of stars and planets, for example, here. So here, if you go out on a dark night in a dark place that's much darker than Baltimore or most places on the East Coast, but if you're lucky, you'll have access to a dark place like this. You can see the Milky Way. Yes, up here is let me see it here. I have the laser. Yeah. Up here, you have close to the center of the Milky Way. And you also see that the Milky Way is, there's a bright stellar background field, but there's lots of dark clouds in it. Those dark clouds, of course, consist of gas and dust, and this is where stars form. So you can zoom into one of the places. Let me go back here so you can see here. You go to a better image here. You zoom into that region here. Low resolution, as Frank does. You can enhance this. This is one of the nearest star-forming regions. It's about 3 or 4 times nearer than Orion that Frank showed. This is called Ophiuchus. This is an area that forms stars much like our sun, so low-mass stars. But it's really dominated. Again, you can see these streamers here of dust. That's what you see. And again, these are visible images. You can make a bigger telescope. You can make a deeper integration here, and you see more structure here. Again, it's the same region. It's just a longer integration time with a bigger telescope. You can zoom in on that here, and you see more of this dark cloud here, and you can also enhance that. So again, we have dark cloud here. So I want you to focus on this area here. Very dark, right? Not much is going on there. Zoom in again here. Wow. Enhance. Okay, this is very dark. Again, this is a low-mass star-forming region. Once you go to the infrared, let's go a little bit into the infrared. Let's start with that. But also note that you see the dark cloud here, and you see around it there's some light here. This is actually light that's scattered off of dust grains from stars in the surrounding area. So you see a little bit of light there. When you go into the near-infrared, just 2 micrometers or so, it looks like this. So all the scattered light fades away, and you start to see these red things inside the cloud. These are forming young stars that were hidden before. And you see a lot of these more whitish stars. These are background stars, so stars located behind the cloud. But there's more to it than that. So this is just 2 microns. So the Hubble can sort of almost reach this kind of infrared. James Webb can do more. All right. So if you continue a journey into the mid-infrared, into the thermal infrared, this area looks like this. And what you see now is that dust itself starts to shine. So in the near-infrared, you see through dust. In the mid-infrared, dust itself lights up. So here you see these bright areas here. These are actually tiny dust grains that are made of it's kind of like a smog. It's made of complex organic chemistry. Those light up brightly. You also see these red stars now. These are scattered in among these blue stars. The blue stars here are just regular stars. In the infrared, in the mid-infrared, these will be blue. These are background stars, just boring old stars with nothing on them, although, of course, many of them will have planets. But the red ones here, those are stars that have protoplanetary disks around them. So they're surrounded by disks of gas and dust that are circling around them, and those disks are actively forming planets. So when you go to the mid-infrared, it's very easy to pick out the objects that are right now currently forming planets. It's the red ones. And this is an example of what you gain from going to longer wavelengths than Hubble beyond the original galaxy formation case. And so why is it that you see dust at mid-infrared wavelengths? Well, what you can do is you can look at this relation here between temperature and wavelengths. So anything that has a temperature emits light. If it's hot enough, you can get white-hot iron, for example, that emits light on its own because it's hot enough. Right? Stars emit light because they're hot enough. So stars are thousands of degrees on their surface, and so we can see them. If you look at the sun, it emits lights on its own. The Earth that we're standing on is also emitting light, but we can see it because it emits light in the infrared because it's cooler. And so this is just to give an indication of relation between the temperature of an object, different planets in the solar system, and what wavelength their peak emission comes out at. So you have stars here through the visible. Once you go out into the infrared, you have Venus comes here that peaks at 4 micron or something like that. Earth itself, its self-emission peaks at around 10 micrometers. And then if you go out in the outer solar system, you end up in beyond the mid-infrared, what's called the far infrared. So something like Pluto emits most of its light at 70 to 80 micrometers beyond what JWST can do. But you can see that the JWST range here, the Webb range, is perfect if you're interested in looking at things that have room temperature. And of course we are, right, because we're interested in looking at planets with room temperature, for example. We're interested in understanding dust and material in planet-forming regions that is much like what we're surrounded here in this room. So the lesson is if you want to look at cool things, you want to go to the infrared, and particularly the mid-infrared. All right. So in terms of size for that, so again, you want to be cold, you want to be big. This is James Webb compared to Hubble. They're actually about in a sense the JWST is not that much bigger. It's actually in terms of mass not that much different than Hubble. But because it has this sort of modern design with no baffle and dominated by a sun shield, which is really very thin layers of insulating material, you can get a much bigger telescope for the same kind of mass. Here is the design related to keeping a telescope cool. So you'll have this side here, which is always facing the sun. It's a warm side, and so that contains the spacecraft, communications, computer, all those things. It's actually quite hot, about 185 degrees Fahrenheit. And then it has a cold side here with the science payload, as we call it. Has all the optics. Light comes in here, bounces off the primary, goes to the secondary, goes into this package here, which is the instrument package. So all the science instrument cameras and things like that sit behind the primary mirror here, and it's also on the cold side, about minus 400 degrees Fahrenheit. So you can imagine the temperature gradient across here is enormous through these 5 layers of sun shield. It's quite an engineering feat to make that possible. So what do you get from having a large telescope that is cold in the infrared? Well, we can compare in the mid-infrared, what Webb can do compared to what has been possible in the past. For example, with the Spitzer Space Telescope that you may have heard about, which is NASA's last infrared telescope, which was an 85 centimeter mirror, right? So just over a couple of feet. So if you look at the science case where you're looking at star formation, the star forming region I showed you and many others, and Orion itself is all contained within this little circle here in our galaxy. It's quite far. It's about 8 kiloparsec to the center. Once you go to Webb and you apply that to the same kind of science, looking at, say, young stars, how far away in the galaxy can you do the same kind of science that Spitzer could do in the solar neighborhood? Well, it expands our horizon like this. All right, Webb will allow us to do the same kind of science, but across the galaxy to completely different regions. We can look at star and planet formation near the galactic center. We can go to the other side, look for what happens if you're out in areas where you don't have as much dust, where less was formed, where it's more quiescent. We can really understand planets and stars in a galactic context, in a galactic sense. All right, compared to people, this is how big it is. So this is a model. Was at Goddard at this point here. You see some of the people who've been working on it. So it's about tennis court size once it's fully deployed. Of course, you can't fit that into a rocket. So Webb will be launched by the European Space Agency on an Ariane 5 from Kourou in South America. And so here's an example of that. And you can look inside the Ariane 5 fairing here, and you can see how Webb will be all folded up. The sides will have come back from the primary mirror in orbit. They get folded out. And the sun shield is also folded up into two pallets that sit along the mirror. So it's quite an engineering feat to make this all fit together so it can fit inside an Ariane 5. There's a lot of progress has been made on the telescope. So here's a recent image this is from Goddard when it was still there. Fully deployed science payload. You can see the golden mirror here covered in gold for the best reflectivity in the infrared. That's why it's covered in gold. You can see the secondary up here also covered in gold. This is the instrument module. As you can see instruments that are bolted onto the sides here. So it has 4 instruments in here. We'll show you an overview of those a bit later. Here you can see the instrument package put in place behind the primary mirror. After it was all completed, the science payload at Goddard, it was transported to Johnson Space Center in Texas, where it underwent extensive tests with inside this big cryogenic vacuum chamber. Had to be very big. So this was originally built for testing Apollo, and so the whole science payload was tested all together in there, and that test has just been successfully completed, and it's out of that chamber again. And here you have the sun shield. There's a spacecraft bus underneath here with all that. Basically, these are the 2 pieces that are left of the observatory. So the science payload here will be shipped to Northrop Grumman in California, where the sun shield is, and it'll be mated together, and there'll be a number of tests all together with the spacecraft all together. And for the first time, you'll be able to see the whole thing together instead of looking at artist's impressions. And that's essentially the last step, that integration and testing. Then it'll be packed up and shipped to South America for launch, which is slated for the second quarter right now of 2019. At the end of, you might want to stick around to the end of this presentation because we have a very cool little video that shows the assembly of this. So that looks nice. All right, so there's a number of science instruments in the observatory, namely 4, called NIRSPEC, NIRCam, MIRI, and NIRISS. The point of this here is that this is what is called a focal plane. So essentially, when you point on the sky, each instrument points at some place in the sky at the same time, but not the same place. So here NIRCam, that's a near-infrared camera that will point at this part of the sky. MIRI, which is a mid-infrared instrument, points at the sky at the same time, but a slightly different spot. So it's actually possible to operate more than one instrument at the same time. You can take pictures with both NIRCam and with MIRI at the same time. They're just looking at slightly different spots in the sky. And if you're smart, you might, let's say if you're mapping a larger region by stepping the telescope, maybe over here, taking another image, stepping it over here, taking another image, stepping it over here, taking another image, and so on. You might have an overlap region where both instruments are taking data once you collect everything. And so there are observing strategies that do that. NIRSPEC does spectroscopy in the near-infrared. And NIRISS here, that's the instrument that'll be, or a lot of that instrument will be used to take spectra of transiting exoplanets. And Bonnie is going to talk a little bit more about that later. An important part of Webb compared to Hubble is that it's not just imaging. There's, of course, a standard imaging modes along all the wavelengths, but it has lots and lots of instruments that do spectroscopy. And why do you do spectroscopy? Well, imaging typically will tell you where things are, but spectroscopy will tell you what they're made of. Right? So if you're interested in, say, looking at what's the composition of a planet-forming disk or a young star or a galaxy, you take a spectrum of it and it will really reveal what's there in particular. Like, for example, so if you're interested in if there's water there, you'd need a spectrum typically to tell you that, and also will tell you properties of that. For example, how hot it is. And so we expect to be lots and lots of spectroscopy done with Webb. All right, so that's the end of the telescope part. I'll hand it on to Bonnie. Talk about the science.
Thanks. All right. Okay. Hi, everyone. Okay, so yes, I'm going to talk about the science today. And there's, Klaus was talking about how great of a history Webb telescope has had in coming to what it is today. And it came up, the original cases for this, science-wise, were very far away from home. There are these early galaxies. And then as the cases all developed, the science cases developed, they really settled on 4 big topics. So I'm going to take you guys through these 4 big topics. One of them still remains the first light in the universe. So some of those first galaxies to form in the universe, how did that happen? How do those galaxies then grow over cosmic time? Some of that work is motivated, again, by Hubble and other telescopes looking at all these different epochs of galaxies. Then we come to how do stars and planets form? We're getting closer to home and smaller and smaller. Tell you guys a little bit more about that. And finally, what are planetary atmospheres made of? So over the course of all of the science and the science case made for Webb as it was being developed, we discovered exoplanets. And we started looking at them, and we developed techniques for actually being able to probe their atmospheres. So these 4 big themes may seem obvious to us right now, but it's been such a long journey with a lot of people involved that these weren't necessarily what we thought we'd be able to get out of this telescope when it first started. I'll also add that, like Hubble, I'm sure even more things will come out of Webb. So back to these first light and the epoch of reionization. So this is a graphic of cosmic time, basically. So we start all the way over here with the Big Bang. Okay, who's heard of the Big Bang? Hands? Okay, good. I see a lot of regular faces out there too. So okay, I figured you guys knew. Okay, so the universe starts basically. Okay, then it's just a big soupy mess. Basically, that's the technical term for it, a soupy mess. And you go through what's called radiation era and the dark ages, and then photons come flooding out. And we call it the epoch of reionization. So from that, we start being able to, so that from this epoch of reionization, particles start coming together. We start getting little protons and neutrons. And those early, that early stuff, the hydrogen and the helium starts forming some stars. And eventually all that stuff comes together and forms those first galaxies. Okay? And then from there we have, a whole bunch of stuff happens, and then we have the beautiful jewel box, gem box that we now have of galaxies in things we've seen that are part of popular culture, like the Hubble Deep Fields. So you regulars, I'm sure you have the lithograph of that. So give you guys a kind of an interesting view of what I just talked about, but with beautiful animation. You see stuff starting to, all these little stars, these first stars starting to come together. Eventually we get lots of galaxies forming. We get this kind of thing happening. And this is what we're ultimately looking for. We're looking for these first stars and galaxies to form, eventually start populating the entire universe, gravitationally interact, and hopefully we can see the light from those. Okay, and this will give us a greater appreciation and better understanding of what's going on out there. How are all of these galaxies forming? How are they evolving? What do they look like as they're evolving? So right now with Hubble, we've been able to look back with things like the Hubble Ultra Deep Field. Back even further with special projects like the Frontier Fields, which use gravitational lensing to be able to probe even farther back toward more distant galaxies. But really, all we've seen, or maybe, if you compare it to a human lifespan, something like a toddler. Okay? Maybe an infant, but maybe like 8, 9 months old. What we want to see are those baby pictures, those infants, that newborn. And we want to see that chubby, squishy little face and see what exactly the full lifespan of galaxies has been in our universe. So that's really important to us. And you see just that to get to this, a point today where we can look out through any soda straw out into the universe and see a jewel box of galaxies of all different types. So, and to be able to look at those galaxies that are closer in and more modern or contemporary and see what is going on inside of those galaxies. So this comes back to that second science theme of the galaxy evolution and what galaxies are looking like today. So, you see, it's perfectly divided down the middle. This is the infrared side, and this is the visible side. So you may have seen this side of the whole thing, the visible side, because I believe we also have beautiful Hubble images of this in the lithographs that you may have received at Public Lecture Series. You can see these bright spots of star formation in here. You can also see these dark dust lanes here. That's all the dark parts here are those dust lanes where the visible light of what's going on in this galaxy can't get through to our eyes or to Hubble's eyes. It can't pass through that dust. But when we look in the infrared, all that dust is glowing, so we can see what's going on with that dust. So you see that these dark lanes here suddenly become the brightest thing in what we're looking at in the infrared. So that's what we're hoping for with Webb, is we're going to study these sorts of things. We're going to look at these dust lanes in nearby galaxies and look for what's happening there and how they're glowing and map out all that dust and learn some more about it. Okay. Third topic that I mentioned earlier was the formation of stars and planets. And I think this is one that really strikes people's imaginations because we're living it every day. You're living on a planet in a solar system that has a star. And so every day you can look up at the sky and think, wow, how did that get there? How are we here? And on a very everyday level, it's there. So what we're looking at here is something that Webb will be able to look at, which would be a newborn star, a forming star. And with a forming star, you get this big disk of gas and dust around it. You get jets coming out of it of really, really hot gas particles, things like that. Then inside you have the new star forming. So I'm going to take this. Yeah, there we go. Oh, it's on repeat. I didn't realize you did that. Thank you. So we have this slider here that takes you from the visible to the infrared of this image. And you can see those jets I was talking about. When you look at it in the visible, all we see is that new forming star right there. The rest of it is all dark, dark dust because we can't see visible light coming through it. But in the infrared, right here, you get to see those jets become visible. And so we can learn more about how these stars are forming and how what processes are happening and how they're affecting the environment around those stars. One of the other things we can look at, as Klaus mentioned earlier, is spectra. So doing spectroscopy, I'm sure many of you regular public lecture series goers have heard about spectroscopy a lot. Looking at what stuff is made of, what's really going on in there. So you get a taste of a couple of things here with Webb. New ways to probe these disks of material forming around these stars. So the new stars have big protoplanetary disks, okay? You can see them up here. Do I have a thing? Right there, yeah. With the star around it, with a big disk, you know, kind of like a plate, a frisbee, something like that around it. And what we can do is we can start to probe what is going on in those disks. And by probing what's in those disks, we can find, with wavelength of light, you see the spikes are telling us what's there. You see a couple interesting places labeled here with different types of molecules. So you see carbon dioxide there, something that maybe you don't want some HCN in there. You wouldn't want it in your house anyway. So then we have. So that's an interesting way to probe it and see what's going on there, because seeing what stuff is made of tells us part of how it's made and maybe how things evolve. Because you can start out with disks, you know, different stuff's going to form in different places in the disk. As you get farther away from the star, the disk is going to get cooler, and so maybe you get more ices, stuff that can live as ice farther out at cooler temperatures. And then maybe that means a different type of planet could form. Maybe that means liquid water or frozen water could hang out for longer. So all those things are building this model of what we expect in a solar system as it forms. One of the other things we can do is, I don't know, is it? Hang on, oops, sorry. And Klaus mentioned this a little bit too, he had an image of it, was a coronagraph. So that's basically blocking out the light of the star to see what's happening around it. And I think I have another image of that coming up. As I talk about planetary atmospheres. So that's that fourth one, planetary atmospheres. And this is one of the ones that's, you know, it's a field that's really gotten big in the last decade, probably in the last 5 years even, as we explore these worlds. And we've gone from being able to just see hot Jupiters to being able to see what is going to be happening in atmospheres of terrestrial type planets around other stars. And that's really the promise of Webb. So who here heard about the TRAPPIST system? Okay, so this came out about a year ago now. It's a star with 7 planets around it. Many of them are around maybe a little bit bigger than Earth size. They're all in what would be, or some of them are in what would be considered the habitable zone of that star, so able to have liquid water on them. One of the big cool things that Webb can do is when we find systems like that to go and probe those atmospheres. And I'll show you a little bit about how we do that. You can do this with Jupiters too. So what we have here is the same. This is the same system, okay? Just 2 ways of looking at it. One of them is what you'd see if you were in the system. You'd see a planet coming around, orbiting around its star, going to the backside, okay? But down here is what we'd see if we just looked at the light coming from that system. We would see you see where it dips there? That's where the planet went in front of the star and blocked out the light of the star. But then when it goes behind the star, you see there's another little dip. That's because this planet is shining in its own light. So when it goes behind the star, we're losing some of the light of the whole system because the star is blocking out the planet. And in doing this, in doing this, what we're really doing is being able to probe what's first of all, there's a planet there. Second of all, what is in that planet's atmosphere as it goes in and out, because we can also do this spectroscopically. Okay. Next, we have, I mentioned this earlier, coronagraphy. So one of the cool things the Webb can do is to look at, directly image planets around other stars. Not just look for the dip in light. So, to give you a comparison point, this is what Earth looks like compared to the sun. So it's teeny, teeny tiny. And if you can imagine if it was out here, it would be very, very dim. It's like a little firefly next to a bright street lamp. Very difficult to see unless you hold up your hand and block out that street lamp, and then all of a sudden you can see, oh, there's like 5 fireflies right there. So that's kind of what's going on here. We can find exoplanets. You see where they are here, but you can't see them, right? So hold up your hand, block out the light of that star, and all of a sudden they are revealed. We get these exoplanets here, which we've seen, this is from the Keck telescope, but which also has a coronagraph, but Webb will have a coronagraph and be able to do this type of measurement too. So we're hitting it from all angles with Webb. It's gonna be a workhorse for characterizing exoplanets. So far, many of the space telescopes we've had, and even some ground-based ones, are all about detecting exoplanets. We're there. We know exoplanets exist. There's a lot of them. They're very exciting. We now know that on average in our galaxy, every star has 1 planet. That's incredibly exciting. That's amazing. But we've also seen that there's a lot of types of planets that could be out there, and Webb's job will be to characterize those and figure out exactly what's going on with these different systems. And to bring it back home, ultimately help us figure out, is our system weird? Are we typical? What's going on with Earth? What's going on with our solar system? Okay, I mentioned characterizing us and are we weird? One of the things that probably leads us to think we're kind of weird, some people call it special, is we have life on Earth. And while Webb is not a life finder, its mission is not to find alien life anywhere. One of the things it can do with spectroscopy is to study these atmospheres and look for various molecules that are abundant in those atmospheres. And this tells us about what's going on there. So, for example, if it finds carbon dioxide, that could mean that, things are breathing the way that we breathe, or it could mean that there is volcanic activity on that planet. If there's methane, there could be some sort of natural geologic process causing that methane, but there could also be the presence of anaerobic bacteria, which, ooh, exciting. And of course, water vapor might indicate some sort of liquid water on the surface, which then would indicate habitability. Of course, none of these things guarantee that there's life on these planets, but it's all about building the case, right? We're still in a fact-finding mission. That's what science is. So we're trying to just find what we can, put the pieces together, pieces of the puzzle. Okay. And with that, as we're putting the pieces of the puzzle together, I'll turn it over to Alex so she can talk about the legacy.
Thanks, Bonnie. Okay, so the final piece of the puzzle. Webb, as Klaus explained, was built on Hubble's legacy, and as Bonnie has told you about the science of the mission, it's going to be incredible and really leave its own legacy. And just like Hubble found galaxies in this area of the sky that looked like nothing, and just like Hubble found exoplanet atmospheres, Webb will find things that we can't even anticipate. And this is really mind-boggling, but how do we get there? So as Klaus mentioned, this has been more than 20 years in the making. So if we're here today and it's launching in about a year and a half, that is only 10%, less than 10% of the timeline that people have been working on this mission. Here's a few of the highlights of that timeline pulled out. That image, that beautiful napkin drawing that Klaus showed you before, is right around here in 95. So again, over 20 years ago. People who were born in 97 are now allowed to buy alcohol. Oh my God. So this is really, we're all really feeling this. I remember when I was an undergraduate and Webb was gonna launch in 2013. So now it's gonna launch in 2019. And so here in 2002, it actually got named the James Webb Space Telescope. Before that, it was approved as the Next Generation Space Telescope. And since then, we've been doing construction. We have the complicated instruments. We have that giant folding primary mirror. We have a sun shield that is, layers with thickness smaller than a plastic bag. And all of these things have been built, tested again. The sun shield, I heard, was folded and unfolded 5 times to make sure that, despite being very, very thin, so that it was less weight, it's still very strong and can be unfolded in space safely. And as of only a few days ago, there was a press release out of Johnson Space Flight Center that said that testing on the optical telescope instrument, which is that beautiful primary mirror you see, and the instrument module, so all the instruments on the back of the primary mirror, everything's good to go. It is now being shipped to California. So this is the timeline of people who have been working for over 20 years on this telescope. Well, why? The real mission here, despite all of this engineering feats, is the science that's coming out of it. And there have been people who've been thinking about the science for more than 20 years. The science portion, the science observations that will be taken over the course of Webb's lifetime fall into 3 different categories. The first category is called guaranteed time observations. I'll explain what each of these mean in just a second. The second category, and this is, so guaranteed time observations, these are people who've been working on the mission since the beginning. They get this time. Then there's early release science observations, which the call for that and the release of those observations was just made in November. Or the release of the observations, the call was made earlier, but the release of what those targets are is just made in November. Everything's available online if you'd like to know what the telescope will be looking at. And all of these will be taken in the very beginning of the telescope's mission lifetime and made available to the community so that people can know what the telescope can do immediately. And then finally, we have what we call GEO, or General Observers Time, and this is open to anyone in the entire world. It's not just Space Telescope, it's not just the US, it's not just people affiliated with NASA or ESA or CSA, any of the space agencies, it's anyone. Anyone in the world can propose for time on this Space Telescope, and that is the same for Hubble. Although all of these things are vetted, so you can try, but you might not want to spend your time because there's a lot of really qualified scientists who are going to be going after this time and do some great science with it. So as I mentioned, here we are today. We'll launch. About 6 months later, we'll actually start to get data out because it takes a while to get out 1 million miles into space. It takes a while to open up this big, beautiful telescope. It takes a while to cool down the instruments because they started here on Earth and then they get out in space and some of them are operating at 7 degrees. So all of that takes a while. It's going to be many months between when we launch the telescope and when it's ready to give us science. But when it does that, it's going to give us these 3 different types of science. And I apologize if the colors aren't super clear here, but this is green, purple, and pink. And again, the green observations, the early release science, will be the first observations taken. They'll all be taken in the first few months and immediately made available. And this is kind of a unique thing, but it's really great. It means scientists put in a lot of work to take observations that then are immediately available to everyone to look at and say, what can Webb do? How can it do it? What's its capabilities? How do we use it best going forward? And then you have these guaranteed time observations that will all be taken in the first few years. And then the general observer time, the time that's open to the entire world, or the entire astronomical community is really who will be using it, goes on for the lifetime of the mission, which is guaranteed 5 years, hopefully up to 10 years. So about those programs a little more, again, there's people who've been working on this for over 20 years. And they get some time automatically on the telescope because they put in the grease work, they put in the legwork. So those are called guaranteed time observations, and that's going to be a chunk of the first couple of years of observations. A very small portion was a very competitive selection for what we call early release science, and these people get to look at objects in the sky that they want to look at, but they don't get to keep the data, which is we call it proprietary. Normally, you get to keep the data just for you to work on for a little bit. These people said, no, I'm going to propose, I'm going to find things out in the sky, and I'm going to share it with everyone immediately so that everyone knows what the telescope can do. And so you're going to see a lot of stuff coming out of these, sort of soon after telescope launches and comes alive. And then finally, we have the general observer pool. Now, all the topics that Bonnie covered, from solar system, exoplanets, protoplanetary disks, assembly of galaxies, first light, the first galaxies, lensing, gravitational lensing of objects, things in our solar system, asteroids, direct imaging of exoplanets with coronagraphy, transmission spectroscopy of exoplanets, all of that is covered in is going to be covered in all three of these programs. So while there is a distinction and a reason that we have all of these different things, really, you're going to see all of this great science coming out, and it's going to cover the gamut, and you're not really going to know. But this is real. There's a lot of people who've been working really hard on this on behalf of the community, on behalf of this giant space telescope. So from this and looking at the science, well, where are we now? We're here today, and let's give you a little bit just what to look forward to in the next 2 years. So right now we are here, well, we were just past here, fall of 2017. We finished our instrument and mirror testing at Johnson Space Center. That went really well. This is a beautiful picture that was actually shared. I believe it was the Atlantic magazine. There's a few people who shared this as one of the hopeful images of the year. Like they put together 35 hopeful images, and this was one of them because this is what our society can do and where it's going, really tackling these feats. And so this was after it came out of Chamber A. Next, it's going to Northrop Grumman Space Park out in Redondo Beach, California. Northrop Grumman will take this giant sun shield, put it with the telescope element, add this, what we call the spacecraft bust, put everything together, and if you happen to be out in Redondo Beach sometime early in the summer, late summer, early fall, you can go maybe see this thing all fully assembled, and it'll wow you, because it's very amazing. Next fall, they'll complete the integration of the spacecraft and the instruments and the optical telescope and the sun shield, this giant thing. They'll pack it up, and they will send it on its way to French Guiana that is launching this giant rocket, the Ariane 5, next spring we'll just say spring. And then it will be operated out of this building. The Mission Operations Control Center is just up there. And that is what it looks like. You probably can't go up there, but that's what it looks like, so you're not missing much. Now you've seen it. It's a bunch of computers, because that's what we do nowadays. So after it gets launched from here, it'll go out into space. It'll take about 24 to 29 days to get out to what I think one of you referred to as L2, yeah, Klaus referred to as L2, this Lagrangian point. It's basically just a place where it can hang out and we don't have to keep pumping it to be there. It'll just happily drift in space and follow along with the Earth. At this L2 point, in the meantime, the sun shield opens up, the telescope opens up. If you haven't seen the deployment, we think some of you have seen it, so we're not showing that deployment sequence today, but if you haven't seen it, every time I watch it, it blows my mind. You are unfolding something the size of a tennis court out in space by itself. It's really mind-boggling, and it takes days to do that. And we're checking all the instruments. It'll take a month to get out here, but then it'll take another 5 months to cool down, check everything out. All of those mirror segments have to be aligned. There's also a really cool animation online of all of those mirror segments going tick, 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 to make sure that they are all looking at the same thing at the same time. That was Hubble's problem, is that it wasn't properly polished. So we took care of that by having lots of different mirrors that we can move around, but you gotta fix them so they move around right. So, and then we find ourselves post what we call launch and commissioning, where we check out the telescope, about 170, 180 days after launch, we are at the most important part, which is where we get all of that good science. And this will be the legacy of Webb, just like Hubble has had a legacy and continues on, and we look forward to the next generation of space telescopes after Webb. But in the meantime, we're going to show you a really cool video of all of this getting put together. And this is footage from, I think, from Ball Aerospace, from Goddard Space Flight Center, from Houston, and also from Northrop Grumman. So this is a really cool time lapse that all of us find really awesome, so we figured you would too. It runs like 2 or 3 minutes. So I guess we should talk through just a little bit. Okay, we can just tell you what's going on. So that's the spacecraft element. So what is going to thrust out into space? Now, I'm not an engineer, but we're going to go through this. So this is in probably Northrop Grumman's clean room, because they did the spacecraft. So then they're going to shove it in a box for a little bit and do some testing on it, and then it comes back out. And you can just see how many people are working on this thing. So now, as you can see, they're starting to attach the pallets that have the sun shield on them. Again, this is all at Northrop Grumman. And so there's these giant things. Again, think of this, the size of a tennis court, this whole thing. And so they're laying down, and there's this special material that very, very, very thin, but very durable and reflective, to get rid of all of that heat from the sun, from the earth, from the moon that we don't want, because we only want heat from objects out in space. So this is the frame of the sun shield. It's a nice, cool kite, because why not put a giant kite in space? And then you can see they're adding the layers of the sun shield and spreading them out. Really, really thin, really slow. This is a time lapse, so. And you can see they're lifting up all the layers. The layers do have spacers in between, so they shouldn't catch on each other as the whole thing's deploying. All of this has been thought of multiple times in multiple ways and tested multiple times. As you can see now, they're folding up the pallets of the sun shield for the way that it's going to be packed for when it goes into space. The actual mirror will be in the center here with the instrument module. But right now they're just testing the sun shield. And they're putting in a faker. That's the official term for it. So this just simulates the weight of the spacecraft. And this is all going to work in space on its own. We wish. So now they're showing how this center part, to deploy the sun shield, everything's folded up. It's folded up in these pallets and then stacked up. So then they have to unfold the pallets, pull out into the kite shape, and then pull up the center part and all of the layers, so that there's these 5 layers and that they sit separate from each other so that they don't conduct. But instead, just each one of them provides a blocking. And then here they're tightening the sun shield to make sure that it'll stay in that configuration and it doesn't rip. And it doesn't. And actually you can see some of the structure on the sun shield there. You could see that it wasn't a flat piece. There was some what looked like crosshairs or some plaid stuff. Those are called rip stops, and it's actually designed so that if there was like a tiny micrometeorite that flew through it, it would just break one small part of it. It wouldn't rip the whole thing. So it's I mean, this is NASA. They thought of some things. So I think that is it, and we'll take questions.
Are you looking at the for a cell string?
I'm just sending off the chat.
Okay. I don't know if we can handle this audience.
I'm sure you guys
He's always the question moderator.
Scary.
like to be up here and help. Okay, I'm sure we have lots of questions right there. Go ahead.
So there seemed to be some confusion about the actual launch site. Is it Peru or is it Guyana?
So the question, I have to repeat the question for the webcam. That's my main purpose here. So, so what is the launch site? Is it Peru or is it Guyana?
It's Guyana. It's Kourou is the area in French Guiana. Sorry. So it sounds like Peru sometimes. It's Kourou.
It's a European spaceport in Kourou.
Okay, all the way in the back.
So, will you please go back to the slide where you were demonstrating what kind of things you can see with the James Webb Space Telescope, like that with the star, with the nebula that forms stars? I have a question about that.
Okay.
Okay, well, she finds it. Let's take another question. There was a question down front.
Yeah, what is the probability that a star has a planet?
What is the probability that a star has a planet around it?
In our galaxy, it's on average one planet per star.
I would say
So-
it's an average at least one.
At least one, right? So you're going to say I've never heard it said as what's the probability a star has a planet, but so basically everything has a star. Everything has a planet. So at least one.
Okay.
So for everything you see up in the night sky, you're looking at a planet as well as a star.
All right, have you got the slide?
Okay. Is this the one you were talking about?
The first one you clicked, like the one with the zoom in. With the zoom in. Yes.
I want to make sure.
Yes, that one.
That one, okay.
Now, go back like a few zoom-ins.
How about you ask your question and we'll find the right thing. So,
So there was this thing in one of the. Oh, there it is. You passed it. It's right. That
Oh.
thing that it kind of looks mechanical. I was wondering if you knew what that is.
so what is that interesting thing in the upper left
That's
there?
that's a good question. That is almost certainly a reflection of the optical element of the telescope. So you can see the primary mirror and some of the rods that the secondary mirror is hanging on. So if you have something very bright in your field, it's just a camera reflection. It's the same if you take a picture of something bright like the sun with a regular reflex camera. You get a reflection somewhere in the system, and you'll get a little image of your aperture.
Okay, over there.
Data transfer from L2 back to Earth.
So what's the rate of the data transfer from L2 to Earth? How fast is the interplanetary internet?
Let me see if I can remember the exact number. The data recorder is a few tens of gigabytes, and it gets dumped once a day or so. So the data rate is pretty fast, but it's not super fast.
All right, question down here.
How much of the time was spent be observing and rest of, out of the, like, 24 hours a day?
All right, so what percentage efficiency do you get for observing versus, say, calibrations and other testing and such?
Wow, some good questions here. So it really depends on what you're observing, right? So on the for example, in the science cases of looking for faint galaxies at the edge of the universe, where you're going to park the telescope in a space and just make really long integrations, efficiency is about 70%. Of course, it's a very sensitive telescope, so there'll be lots of science done with much brighter targets where you don't spend as much time, and then it'll be worse than that.
Okay, so we got a question from online. Is the coolant going to be a significant constraint on JWST observing? And since I know the answer to the question, I'll ask the follow-up question. If it's not the coolant, what might be the constraint on the lifetime of the telescope?
Right. So there's no coolant that's a consumable at the telescope. There's one cooler for MIRI that's an active cooler, but it's a closed cycle cooler, so it works like a refrigerator. It's a pump that compresses a gas, and so there's nothing lost. So that's not a consumable. The main consumable is propellant. So the L2 orbit is not a stable orbit, so you have to use essentially rocket fuel to keep it in place. You also have to use fuel to, so basically, because you have that big sun shield, it actually gets pushed by the solar wind, so the particles from the sun. And so that if you didn't do anything with the telescope, it would actually start to rotate and then eventually tumble. And so you don't want that. So you have a reaction wheel on it that spins up to counteract that rotation. Eventually, that reaches its limit, and you have to make a burn to spin that wheel down again. And so that also uses propellant. So the ultimate consumable is rocket fuel.
So the question, is then that they ask is, so what do we expect as a lifetime for JWST? How many years? How many decades? How about that?
Yeah, we wish you counted in decades. The requirement is 5 years, but it's not going to be launched with less propellant than for at least 10 years. And so that means that it can live for 10 years, even maybe a bit more. But it's possible that parts of some instruments might break between the 5 and the 10-year mark. Hopefully not.
Okay, in the middle of the audience there, in the black sweater, there. Yeah.
So could you talk about the resolution of James Webb compared to like Hubble?
So what is the resolution of James Webb compared to Hubble?
Right. So you can calculate that fairly easily. The Hubble has a 2.4 meter telescope, and JWST has a 6.5 meter telescope, and so the resolution scales linearly with that. It also scales with wavelength. So let's say the mirror of Webb is about 2.5 times the size of Hubble, and so at the same wavelength, the resolution will be 2.5 times better. But you're not at the same wavelength. You're at about 2 to 5 to 10 times longer wavelength, and so then you scale back down again. So that's a complicated answer. The simple answer is it'll be about the same resolution as Hubble.
So those pixels we saw before about Hubble before your presentation, would they look the same then if seen through James Webb?
It would have the similar sharpness, but it will look quite different because you'd be looking at say dust instead of stars.
But as he said, at the same wavelength, it'll be 2.5 times sharper. Okay, it'll be a couple times sharper. It's just if you're looking at the longer wavelengths, it'll be about the same. Okay, so in front here.
Will it be able to look anywhere in the universe, or will it be restricted because of its position relative to the sun? Or something?
Right. Yeah, this question came up on the chat as well. They were worried that Webb would be restricted because it has to point away from the sun in what it can observe.
Yeah, that's an excellent question as well. So it's a bit of geometry there. So it orbits, Webb orbits the sun along with the Earth. And so the answer is actually that it can observe every place in the sky. But because the sun shield will point to the Earth, the telescope will point either up or down or all the way around, like a circle like that. So you imagine you'll have a circle in the sky that looks like that. Over the course of a year, that circle will move all the way around and scan the entire sky. So if you have an object that is very close to the ecliptic, let's say the sun and the Earth, if you have a target that's very close to the ecliptic pole, you can observe it all the time. If you have a target that's pointed directly away from the Sun-Earth plane, you can observe it twice a year. Right?
So does that mean For the really long observation times, you can only look, at the year.
Well, yeah, okay.
That question. So if you want to do a really long observing time, are there special points in the sky you have to be pointed at?
Yeah, so it has to be a very long observing time. So any given point will have a couple of weeks of potential time.
And if you really want a cool way to visualize this, stay tuned to those social media accounts that Frank shared earlier. In about a month, maybe a month and a half, there'll be a really cool animation to show you exactly what Webb can see in the sky and explain that circle rotating that Klaus just mentioned.
Okay, other questions over there?
How long will Hubble operate? Will there be a time when both are operating at the same time?
So how long will Hubble operate, and will J2ST and Hubble overlap?
Somebody else can.
I'll take this one. Okay, so Hubble's doing really well. April is Hubble's 28th birthday, and so we are expecting good things. It's in good health. It looks good. So yes, we anticipate that Hubble and Webb will observe simultaneously. And one of the cool things you can do with this, I'm putting in a plug for my own thing here, is because they're about 1 million miles apart, think about your two eyes. And what does having two eyes buy you? Yeah, depth perception. So one of the cool things we might be able to do with Webb and Hubble at the same time is look at objects and be able to get some depth perception there, especially things close to us. So solar system objects, things like that. I'm a planetary person, so I'm really into this idea. Okay, that's why I kicked Klaus out of the way. I wanted to answer that one.
But my understanding is it won't be good much beyond Jupiter. Maybe the asteroid belt will be we'll get a little bit of stereo to the
But we
asteroid
have
belt.
cool things like the active asteroids that are shooting out jets, and
As I said,
you get some three-dimensional information on that, and you
get some great stereo views of rocks.
whatever, man.
It'll be like going to Mars again. All right. Sorry, we're just having fun. Question here.
Are there research proposals already lined up and approved?
Another question that came up in our chat online. Are there research proposals that have been submitted and or approved? We know what Webb is going to look at first.
We know some of the things that Webb will look at first. So these are what Alex was talking about, so I'm going to let her keep answering that question.
Okay, I will just pull up the slides because, I do extra work. The answer is yes, we have these proposals. And so two of the three types that I mentioned, this is fun. Two of the three types that I mentioned, the GTO programs and the ERS programs, the guaranteed time observations, which is that time that we give to those people who've worked on this for 5, 10, 20 years. This purple graph here of people working, they get time. They get a couple of thousand hours in the first couple of years. And then this director's discretionary early release science was picked by the director of the Space Telescope Institute as science cases to demonstrate the capabilities of the telescope, and will be released immediately and taken in the first couple of months after launch. These programs are already decided. They're available online. There's 13 programs under the ERS, and there's if you break them down into programs, a couple of dozen programs for GTOs under a few key people. The key people who were part of the program from the beginning, they got time and they said, this is what I want to spend my time on. You can review all of this. It's online. If you want that link, come afterwards so we can get it to you. It's long. But all of this information is available online. If you just Google JWST early release science, you'll get an article that explains all of the things. And again, this covers solar system objects, all of the 4 science themes that Bonnie talked about. And we do know these already. These will be decided in the summer, and you'll hear about them probably July. For the first round of general observer observations, from then on, these are already decided and they'll be taken at the beginning. From then on, we'll have several calls for people to submit ideas. And as we get back data from Webb and find out what it can do, that'll spark ideas for new proposals. And so for the lifetime of the mission, we'll keep asking the astronomical community for what they want to do with the telescope, and we'll keep getting answers. But thus far, the programs that have already been approved fall into these two buckets, and you can find them online.
Okay, we have time for one last question if anybody has it. Going once. Hup, take it and go. What's the last question? Make it good, because it's the last one.
So I imagine there's no dearth of observation proposals for current land-based and space-based telescopes. You're going to fill up the Webb agenda. What's the plan for the next infrared telescope to replace the Webb?
Okay. So, all right. So, obviously, there's tons of really cool science we can do with Webb. What's the plans for the telescopes beyond Webb that will replace Hubble and Webb in the 2030s? Who wants to answer that question?
Well, okay, so there's. I don't hurt myself here. So there's the Wide Field Infrared Telescope, which is under construction at the moment, which is a near-infrared telescope that has Hubble-sized, but it has 100 times the field of view as Hubble. So it'll make Hubble-like pictures, but it'll be 100 times bigger. Which is why it's a survey telescope. So that's approved and that's under construction. Beyond that, for the 2030s, there's a process ongoing that happens every decade in the United States. It's called the Decadal Survey. And that consists of the community, astronomical community, getting together and,
So in 2000 was when Webb was given to us.
Right. So the community gets together and they think about what they might want to do for the following decade, in this case for the 2030s. So JWST was the selection for the 2000. WFIRST was the selection for 2010. We need a selection for the 2020s. So there's 4 concepts for new flagship telescopes. And one of them is an infrared telescope that goes beyond in wavelength, even what JWST does. It covers from 5 micron to 660 micron, but it'll be between 1,000 and 10,000 times more sensitive than anything has been done before. So that's a new frontier. It's called the Origin Space Telescope, and you can Google that and look it up. So that's one of the concepts. Now, there are other concepts as well. There's also a concept that's called LUVOIR, which is the next optical telescope, which is a 15-meter telescope that's going to follow up on Hubble. So there's going to be some tough decisions to make for the astronomical community of what is the best way to spend money going forward for the 2030s. So it'll be interesting.
Okay, so that's all we have time for tonight. If you have more questions or things, you can come down. The speakers will be here. Next month, February 6th, which is only just a couple of weeks away, the wildest weather in the universe. Let's give all 3 of our speakers a great big hand. Good night.
Sorry, that Spitzer was in the asteroid belt near Saturn. Sorry, I didn't quite hear.
Not much. Hubble isn't great. Okay, Hubble is solid. Nobody in Congress would dare go after Hubble. With the holiday season greeting on it as well. Our second story tonight, finding defects in the star formation factory. Yes, there are people who have to find those defects. All right, so this is the star formation factory I'm talking about. It's called the Orion Nebula. And this is a star-forming region, and there are several thousand stars, about 4,000 stars that have just formed. And when we say just formed, on astronomical timescales, that's 2 million years ago. Okay, so there are stars in the Orion Nebula that are 2 million years old. But not all things that collapse are massive enough to form stars. Okay, so if this is a star formation factory, sometimes you get some defects that are too small to form stars. Right? And it's important for us as astronomers to try and understand when you've got a collapsing nebula, you've got a gas cloud that's collapsing to form objects, what percentage of that material goes into stars? What percentage of the material goes into planets? We really want to know that too, and we're searching that in other ways. But what percentage of it goes into something that's bigger than a planet, but smaller than a star? And that's what we call brown dwarfs, okay? Brown dwarfs range from basically 15 times Jupiter's mass to about 70 times Jupiter's mass, okay? Something that's, and that's when you get what we call deuterium fusion, okay? Now, the main sequence stars are powered by hydrogen fusion. The fusion of hydrogen into helium is what powers the sun and other main sequence stars. But deuterium, which is called heavy hydrogen, that is not a long-term sustained fusion. It will flare up, it will last for a while, and then it will fade away. So these brown dwarfs are extremely faint, and compared to stars, they're extremely cool. They're so cool that water molecules will form in their atmosphere. And you can actually detect them by looking for water molecules. And where do the water molecules show up? In the infrared. So this is just a single filter from Hubble in the near infrared. And those circles are around certain detections of. I checked the weather report here in Baltimore. If there's snow tonight, it's not going to happen till, it's supposedly not going to happen till after 11 o'clock. So we finish at 9:30. You should have plenty of time to get home unless you drove 2 hours to get here, in which case I applaud you, okay? All right. One more minute. Just give a second. We'll be ready.
How much your son scope? He said, oh, don't say I don't want to barrel. That great stuff. I mean, we're looking midday, right in the sun. Everything.
Just for you. Okay.
I have an old source phone. That's very nice. I had an 8. I had an 8. That original orange tube. Orange tube. And it did some nice stuff. The problem is, I think it's really mountain. But I was looking at this. I had a
Yes, there is. Breathe slowly down.
All right. Calvin, we ready? You got the thumbs up. Okay. And now the news from the universe for January 2018. Our first story is a month old. It is our Yuletide stars. So every year we have to put out something for holidays, right? And they go through a selection process and they come up with something. And this year they came up with the globular cluster Messier 79. And this was brought up in our news meeting, and they said, okay, what can we do with this to make this holiday? And we were batting around ideas, and I came up with something. I said, well, we could do this thing that we did, and I'm not going to tell you the idea because it'll show up in just a second. I said, yeah, that might work. And they held me to it. So I came up with an idea in the middle of a meeting, just off the top of my head, and they made me follow through in it. So the team and I got together and we put together a little visualization of this globular star cluster with a surprise holiday theme at the end. So this is one of our normal zooms in on the night sky to show you where Messier 79 is. And it really is deeply hidden. There we start to see the cluster. This is a ground-based version of it. But as we zoom in, you find out that Hubble doesn't see that wide field version. It doesn't even see this version. It sees the very central region of this globular star cluster. And to give you a feel of the 3D, we created this 3D visualization. It has the similar statistical properties as this M79 globular star cluster. And then as we pull out, our idea of a stellar snow globe is revealed. So this will teach me to speak up during meetings. We also created this version, which is just the snow globe spinning, and it actually is on a loop. So you could play this, put this in the background of your holiday party next year, and you could have that snow globe spinning infinitely. Find this web page, and you can see we've got a list of the upcoming lectures. We've got links to the webcasting, which are live when we are doing it live now, as well as links to the past lectures. We've been on YouTube since spring of 2014, and we have been on the STSCI webcasting site since 2005. So we're approaching 13 years of astronomy lectures on our webcasting site. That's one of the reasons I ask you all to give a hand to our webcasting folks at the beginning, because they do such an amazing job in archiving these wonderful talks. You can also sign up for our email list that will send you reminders of the talks every month. This is the email one, which is sort of redundant now that we have the sign up on our web page. You can also, however, send us comments and questions to publiclecture@stsci.edu. Social media, we have Facebook, we have not one, but 2 Twitter accounts. We have YouTube. We have Instagram. We actually ought to get the JWST ones up on here now that we're getting closer to JWST launch. So, yeah. All right. My apologies. It'll be fixed for next month, okay?
That's good. Using Space Telescope right now.
Using Space Telescope right now. I also occasionally post on a blog and Facebook, Google+, and Twitter, and you can get those if you like. Across the street, we have the Maryland Space Grant Consortium Observatory. The Maryland Space Grant Observatory will not be open tonight. If you looked up, you didn't see many stars, if any, on your way in. It's cloudy. Actually, the fact that it's cold is really good, because when it's cold, the air is still, and it'll be a really good night. I mean, some of the best nights observing are when you're totally freezing your butt off, okay? Unfortunately, clouds are never help, whether it's cold or warm, so they will not. They do have open houses on Friday evenings. If you go to md.spacegrant.org, they have this page here where you can find the observatory status. They will post it by like 6 or 6:30 on every Friday as to whether they're opening up on those Fridays, okay? So come back to and visit us in future lecture series, and maybe it'll be open, but certainly you can try every Friday on that. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach. And when you came in, there are lithographs on the table here. Our lithograph tonight is the Eagle Nebula, M16. These are the pillars of creation in the Eagle Nebula, seen in both visible light and infrared light. And this will have special significance for our talk about infrared telescopes tonight. Our talk is... It's not working. All right, so let's go here. Our talk is Webb in 3 acts: the telescope, the science, the legacy. And we have 3 speakers to take care of those 3 parts. And I'll introduce them later, but we're going to get a good look at the James Webb Space Telescope tonight. Next month, we have The Wildest Weather in the Universe by Hannah Wakeford. And in that, she's not talking about just in our solar system, but also in other planetary systems, the planetary systems that we have found, and the weather that we would deduce happens on those planets. On March, we have Mia Bovo coming back again. She's given some wonderful talks the last couple of years, and she decided she was going to have some fun with her title. So it's called Mapping the United Federation of Planets, an Astronomer's Guide to the Galaxy. So she will be using lots and lots of Star Trek references. Okay, but she will also be putting them in context of our actual scientific knowledge of the galaxy. So if you want a combination of fact and fiction, come to see in March. In April, Susanna Deusto is going to talk, and she did not give me an actual topic. She just said, I'll talk about something about cosmology, because everybody loves cosmology. So in the next month or so, I will get an actual title out of her. But you guys do love cosmology, right? Yeah, so you're going to come no matter what. All right, great. If you would like to keep up with what's going on, you can go to our website. If you just put in your favorite search engine, Hubble Public Talks, you'll